So remember, the reason we invented spherical coordinates was so that we could do integrals in spherical coordinates. We've explored the spherical coordinate system a little bit so that we should be able to express the bounds of our regions in spherical coordinates. But remember, the other ingredient we need to do integrals in a new coordinate system is to figure out what is dv in terms of our new coordinate system. So to figure out what dv is, remember, we need to figure out if we have a little box that we make by varying the coordinates a little bit, we need to express the volume of that box in terms of the coordinates, or in terms of the small changes in the coordinates. So let's do that. This is a little bit tricky. So here's the positive z-axis, and we're going to start at a point whose coordinates are rho, theta, and phi. I won't put these coordinates, list these next to the point on the diagram because otherwise it'll get too messy. So remember, this angle down from the positive z-axis, that is phi. Okay. This point is above a spot in the xy plane, so let's put our coordinate, our x and y axes like this. Okay, so this angle right here is theta, and then the distance of this point from the origin, that's rho. And then we're going to change phi a little bit. Changing phi a little bit is going to swing this angle, this point down a little further. So this angle right here is d phi, because that's the small amount that we changed phi. When we change theta a little bit, so that's going to swing this point sideways a little bit. And let's see, it's kind of hard to indicate. I guess the way to do it would be, it's going to be like this. Okay, so this angle right here is d theta. And then, so that gives us, so far we've got this. And then changing rho a little bit is going to sort of move all of this a little bit further away from the origin. So all of these are going to slide out like this. And we get this kind of box. Okay, this sort of wedge-shaped box. So the volume of this box is dv, but we need to express this volume in terms of phi, rho, theta, phi, d rho, which I didn't write. D rho is this distance right here, d theta, and d phi. Okay, so well, dv, it's a box. It's a slightly curvy box, but remember, these changes are all so small that it's not right in the limit where these changes go to 0. The curves straighten out essentially. So the volume of this shape is going to be the length times the width times the height. Okay, and these are what we have to express in terms of our coordinates. So one of these is easy, right? The length of this box, I'm going to call this direction the length of the box, and that's just d rho. So one of them at least is straightforward. For the width of the box, let's call this side length the width. That's the same as this one right here. And that's what we got by changing theta. But right, what we need is a distance, and theta is an angle. So what length is this? Well, this is what we got by changing theta, and if you keep changing theta, this arc sort of, when you change theta as much as possible to do a complete revolution, this arc becomes part of a circle, right? So this length is part of a circle where the angle that we change, the angle is d theta, right? Because that's the change in angle that we use to make this little arc. And the radius Well, we have to figure out the radius, right? The radius of this circle that this point is traveling around is, oh, sorry, I should have drawn this circle up here. It's this up here. The radius that this is traveling around is this distance here. Okay, so what is that distance? Well, that's r, right? Our polar coordinate r, and that's in this right triangle where phi is down here, and right, we have this right triangle. Okay, so the radius is r, and we know that r is rho times cosine sine of phi. Okay, so the arc length of this part of the circle, remember it's just angle times radius. So the arc length, which is going to be the width here, the arc length of this arc is the radius, rho sine phi, times the angle change, which is d theta. Okay. Now let's figure out the height of this box. That's going to be this arc right here. And again, so that we got that by changing phi. If we keep changing phi, this traces out a circle, right? So this arc that we need is part of a circle. And again, to figure out the circle, we need to figure out what the arc length of this part of the circle is. We need to figure out the angle and the radius. So for this one, the angle, well, that was just d phi. And the radius for this circle, well, this circle is on the sphere of radius rho, so it's just rho. Okay, so the height is, again, the arc length of this segment right here, which is the angle times the radius, which is rho times d phi. Okay, so putting this all together, what we get for dv is, let's see, we have two factors of rho, so rho squared. We have a sine phi, and then all our differentials, d rho, d phi, d theta, and you can put these differentials in any order. So this is dv in spherical coordinates, rho squared, d sine phi, d rho, d phi, d theta. For a quick sanity check, let's check why it is that phi shows up but theta doesn't. So if you imagine what shape you get for this kind of wedge for different theta values. So, right. So there's one of these boxes out here, right? And what is changing theta going to do? Well, theta is going to rotate this box around the z-axis, but the shape of this box isn't going to change as it travels around. So the shape of this box shouldn't depend on theta because this box doesn't change when you change theta. So it makes sense that theta doesn't show up in this expression. On the other hand, if we compare what this box looks like for different values of phi, right, when phi is near 0, so we're up at the top, right, this box is going to be very narrow, but if phi is about pi over 2, so we're going out this way, this box is going to look more like this. Right? So the shape of the box does change when you increase phi, and so it does make sense that phi itself shows up in this expression that we got for dv. Okay, so we finally have everything we need to calculate integrals in spherical coordinates. We can describe bounds in spherical coordinates, and we also know what dv is in spherical coordinates, and of course we know what x, y, and z are in spherical coordinates. So we can put all of these pieces together and come back to the original integral that inspired us to start to invent spherical coordinates, and that was this integral. So triple integral of x dv, where the region we're integrating over is the unit ball, x squared plus y squared plus z squared less than or equal to 1. So if if we think about the region that we're integrating over, so I'll draw the z-axis and the x-axis, and the y-axis is going to be out this way. Okay, so let me put this over here. Okay, so dv, our volume element, is rho squared sine phi d rho d phi d theta. Okay, so let's figure out the bounds in this order. So our theta bounds, what theta values do you need to cross to cover this entire sphere? Well, since the sphere is surrounding the origin, you have to go in all horizontal directions to cover all of the sphere. So d theta is going to go from 0 to 2 pi. Okay, now for a single theta value, what phi values do we need? Well, we have to go from pointing directly up all the way to pointing directly down to cover all of the sphere. So that's going to be from 0 to pi. And then what about our rho values? Well, along a single direction, the smallest distance from the origin is 0, and the biggest distance from the origin is, well, the edge of the unit ball, which is the unit sphere, so that's 1. So from 0 to 1. Okay, and then the last thing we need to do is put our integrand in here. Our integrand is x, but remember we need to write x in terms of spherical coordinates. And in terms of spherical coordinates, x is, let's see, it's rho cosine theta sine phi. All right, so here's the integral that we need to calculate to compute the integral over the unit ball of x dv. Notice that what so often happens has happened again. This is a product of a function of rho, a function of phi, and a function of theta. So we can separate, and all the bounds are constants, so we can separate this integral, this triple integral, into 3 separate one-variable integrals. So taking our theta integral, that's from 0 to 2 pi of, let's see, the only place cosine shows up is right there. Oh, I'm sorry, this x in our original, in the problem that inspired us to invent spherical coordinates, this x was squared. So this rho should be squared, and this cosine should be squared, and this phi should be squared. Yes. Okay. So gathering up our thetas, this is going to be integral from 0 to 2 pi of cosine squared theta d theta. Looking at our phi integral, that's from 0 to pi. Let's see, we have a sine squared phi right here and another sine phi there, so that's sine cubed phi d phi. And then for our rho integral, that's from 0 to 1, and here we have a rho squared and another rho squared, so that's rho to the 4th d rho. Okay. So this kind of integral is a really common thing. This is a common situation when you're dealing with spherical integrals, where you have powers of trig functions and then powers of rho. Now, powers of rho, this is easy to integrate, right? This is 1 over 5 rho to the 5th from 0 to 1, so that one's going to be straightforward. But if you don't remember how to integrate powers of trig functions, spherical integrals will be very difficult. So you might need to pull out your Calculus 2 textbook and review how to integrate powers of trig functions. So for cosine squared, the way to handle this one is to use a trig identity. Cosine squared theta is equal to 1/2 1 plus cosine 2 theta. Okay. And then for an odd power of sine, the way to do this is to take 2 of those sines, right? Think of this as sine squared times sine. Okay, so, and then take sine squared and rewrite that as 1 minus cosine squared, so phi, times sine phi d phi. Okay. So for our theta integral, now we can just do this integral. This is 1/2 theta plus 1/2 sine 2 theta from 0 to 2 pi. For our phi integral, we need to distribute this sine phi. So we're going to have integral from 0 to pi of sine phi minus cosine squared phi sine phi d phi. And for rho, of course, now we can just plug in our bounds. We're going to get 1 over 5 minus 0. So for our theta integral, this is going to be 1/2. So when we plug in 2 pi, we get 2 pi plus, well, we get 0 when we plug 2 pi into this sine part. And then when we plug in our zeros, we get nothing but zeros. So it's just 1/2 times 2 pi. Okay, so now we need to do our phi integral. And we'll integrate these two pieces separately. So integral of sine phi, that's minus cosine phi. So from 0 to pi, and I need to put this whole mess in brackets like this. Okay, and then minus, now we need to integrate cosine squared phi times sine phi. And the way to do this is to do a u substitution. Let u be cosine phi so that du is minus sine phi d phi. And that's going, so when we do this substitution, that's going to use up this factor of sine so that we can integrate just using the power rule, essentially. And it looks like it's also going to use up this minus sign. So that will make this a plus, and we're going to get 1/3 cosine cubed